So yes, hello, my name is Connor. I founded a company called Suborbital, and it is all about bringing WebAssembly to the cloud, which is exactly what I'm going to talk about today. So the talk is called Introduction to Cloud Native WebAssembly, and we're going to try to spin through this in 30 minutes, and hopefully there will be time for a demo at the end if I don't take too long with the talking part. So we're going to talk about what exactly WebAssembly is for anybody who may not be familiar with it. We're going to talk about why you would want to run WebAssembly in a server context. And then we'll talk about how and what you might exactly want to do with this newfound ability. So what is WebAssembly? Well, there's actually kind of two answers to that. WebAssembly itself is actually a binary format for programs that have been compiled from various languages. However, people often refer to WebAssembly in the runtime way, meaning that you can refer to WebAssembly as a runtime to execute the binary format WebAssembly. So there's often some confusion, but just be aware that WebAssembly, the format, is separate from WebAssembly, the runtime environment. So the binary format part of WebAssembly is a way for code to be compiled to a binary that is completely agnostic from any architecture, platform, or operating system. And it is a way to represent any statically typed code. So WebAssembly is a statically typed format, and it is a relatively efficient format, which we'll talk about a little while later. And then when you refer to WebAssembly as a runtime, a WebAssembly runtime is something capable of executing WebAssembly code. And some of its amazing properties are the fact that it does execute this code in a very tightly controlled sandbox, a sandbox that we call deny by default, because by default, you cannot access anything from the outside world. You have to explicitly grant capabilities or host functionality to a WebAssembly runtime in order for the code being executed to exit the sandbox in any way, shape, or form. This provides some really great security properties that we'll talk about in a bit. So some people might ask, well, I've heard that WebAssembly was designed for the browser. And you know what? That was how it started. It started as a successor to ASM.js and native client, which were technologies developed, years ago for executing, C, C++, and other languages in the web browser, often by transpiling them to JavaScript. And as a result of this, people realized maybe that's not such a great idea. So instead, they started developing a new way of executing code in the context of a web browser, and that became WebAssembly. Now, what people quickly realized is that the technology that they developed to do this wasn't actually inherently tied to the web browser in any real way. It actually was a generic way to execute sandboxed programs. And so things started to expand. I don't know why this bar at the bottom won't go away, but oh, there it goes. So why would WebAssembly make sense in a context other than the web browser? Well, we like to talk about the three tent poles of WebAssembly. They are performance, security, and portability. But when we talk about WebAssembly in a server-side context, I also like to throw hot loading into the list, as it is a really, really nice property. So we're going to touch on performance a bit in a minute, so I'm not going to go over it too much here. However, security and portability are very important. So we've already talked about how the WebAssembly runtime executes code inside of a sandbox. And this is very useful when you are potentially running untrusted code. It is very useful for enacting the principle of least privilege to ensure that your code is only doing what you want it to do and nothing more. And it also has an impact on supply chain security. For example, the Log4j issue that I'm sure you may have heard of online could have very well been mitigated by capability based security or sandbox based execution environments because the access that these programs were given would never have been granted in the first place, thus making a lot of things easier to manage and easier to secure. And as we already touched on with portability, WebAssembly is a platform agnostic format. And so, you know, even if you use a language like Go, for example, which has really easy cross compilation, well, you don't even need to do that in the first place when you're using WebAssembly because the exact same WebAssembly file can be executed on any platform, any operating system. And the WebAssembly runtime will actually completely abstract away any difference between those platforms. So we don't necessarily like to use the term write once, run anywhere because that was, kind of taken by the Java ecosystem in the 90s and 2000s. But you can kind of think of it that way in some regard. So then hot loading is a really interesting part of running WebAssembly on the server. Because WebAssembly modules are loaded and unloaded at runtime, you can actually fairly trivially swap out the business logic of your application in real time without terminating any processes. It's really quite fascinating when you have the ability to change how your application runs without actually restarting your application, especially in a server side context when you are handling network requests, you have things bound to sockets that you don't want to drop. It can make a lot of things quite a bit easier due to the nature of how WebAssembly is executed within a parent application. And one of the greatest parts is that you can start and stop these WebAssembly modules in microseconds or sometimes single digit milliseconds. It really depends on your use case and it really depends on what you're building, but this can be an extremely useful property, and we'll talk about that more in a second. So on the surface, you might want to compare WebAssembly to Docker, and that's an absolutely valid thing, and it's a very, obvious comparison that you might want to draw. However, the comparison between these two is actually somewhat surface level. These two technologies can solve similar problems, but under the hood, they are extraordinarily different. So where a Docker container is often attempting to emulate an operating system, it it includes things like a file system, user accounts, a networking stack, all those kinds of things. A WebAssembly module, on the other hand, is more like a single program. So there's no, executable binaries. You won't find curl inside of a WebAssembly module, whereas that's a relatively normal thing to find inside of a Docker container. And so an interesting way to think about this comparison is that yes, a Docker image or an OCI container is more analogous to an operating system, whereas a WebAssembly module is more analogous to a single program. And it is absolutely valid to run WebAssembly inside of a Docker container, especially when you're looking at running serverless WebAssembly in Kubernetes, for example. These can absolutely be complementary technologies, and it's not like WebAssembly is a replacement for Docker so much as they, have different strengths and weaknesses. So let's touch on performance. So when we, as people who work with WebAssembly, talk about performance, we often use the term near native performance. And this is something that gets thrown around, but there's absolutely some nuance to it. So the promise of WebAssembly is that you should be able to compile your code and execute it in the secure sandbox at a very, near native performance way. However, this can vary depending on the programming language, the WebAssembly runtime, and a bunch of other factors. So one of the important things to note is that a WebAssembly runtime can execute WebAssembly code in ahead of time or just in time compilation strategies. And this can change the performance characteristics of your application. So consider ahead of time compilation, where the execution begins. The WebAssembly runtime will take the entirety of your WebAssembly module and compile it to machine code before beginning to actually execute the code, compared to just-in-time compilation, where pieces of the WebAssembly code will be compiled as they are needed, which is somewhat more similar to how JavaScript is usually compiled in a web browser, for example. So ahead of time compilation will often give you better performance for programs that are running for long periods of time. However, they will take longer to start up. Whereas just-in-time compiled programs will start up very, very quickly, but may not have the same level of performance over a longer time span as compilation is being done continuously. Now, most WebAssembly runtimes support both of these options, and so it is up to you, the person running the program, to decide what performance properties you care about and choose accordingly. With Suborbital, what we are usually dealing with is serverless functions, which are often, cold starting. They are often executing very quickly. They're often very ephemeral. And so we tend towards just-in-time compilation because it fits the properties that we need a little bit better. Another thing to consider is the differences in languages when you are compiling to WebAssembly. It is really fantastic that you can take all sorts of different languages like C, C++, Go, Rust, assembly script, whatever, and compile them to WebAssembly. However, these different languages have different performance properties, especially when compiled to WebAssembly. So for example, Rust and C have very small runtimes bundled with the language. So this means that there is not a lot of extra stuff added with your code to actually facilitate the running of the code. Whereas something like Go or Swift has a larger runtime included in the standard library or in the language's runtime. For example, with Go, there is extra code needed to schedule Go routines. In Swift, there's a gigantic standard library and a bunch of foundation packages that need to be shipped with a WebAssembly binary when compiled from Swift. So the performance of these different programming language components can affect the performance of a WebAssembly module, partially because it's just extra things that need to be compiled either ahead of time or just in time, but also it can affect the size of the module, and that can affect maybe it takes longer to download or something like that. So startup time is kind of just a consequence of these other things. I will say, however, that the startup time of a WebAssembly module is often much, much better. In fact, usually orders of magnitude better than the startup time for a container. And this lends itself really quite well to the serverless function use cases that Suborbital is usually dealing with. So just to sum up why you might want to choose WebAssembly, the fact that you can compile multiple languages to a common format and execute them potentially all mixed together in a single application is a really attractive property. The ability to hot reload your code without, for example, dropping network connections that are being sent to your server is a really nice property. And the security of WebAssembly is really, really fantastic and allows you to more tightly control the permissions and the capabilities of your code and improve the supply chain security of the programs that you write for the cloud. So, what are some actual real world things that we might want to do with WebAssembly in the cloud? Well, user submitted code and plugins is a very interesting use case, and it's something that we explore pretty heavily at Suborbital. The fact that we can very, very tightly control what code in a WebAssembly sandbox is able to do means that we can more confidently run code submitted by an untrusted source, which is often a user, and we can allow that user to run their own logic and their own extensions, their own plugins within a larger application in a much safer way compared to, for example, running their code in Node.js in a container. I know I've touched on this quite a few times, but it is really quite useful. The ability to hot reload your logic is extremely powerful and allows you to do upgrades and rollbacks of your cloud software really efficiently. And then functions as a service, or serverless functions, is one of the most exciting applications of WebAssembly, in my opinion. And that is all led from the performance characteristics of WebAssembly and the fact that they can start from nothing very, very, very quickly, often in 1, 2, 3 milliseconds, or even less than that. It lends itself very well to ephemeral serverless functions. So, how? I think that's a big question. And I think I've set myself up time-wise pretty well for a demo. So I'm going to give you a quick walkthrough of a basic application built with Atmo, which is our main open source project. I invite you to go check it out on GitHub. Full documentation and everything is available there, so you can try it out for yourself. I'm going to do a quick walkthrough here. So Atmo is something that we call a WebAssembly server application environment. And what it allows you to do is write functions in various languages and compose those functions together in order to form the business logic of a larger application. And this application can be a REST API, it can be a stream processor, it can be a WebSocket server, it can be any number of things. And Atmo allows you to do all of these things with a declarative description of your application, rather than needing to write a ton of boilerplate code in a host language in order to run your WebAssembly. So I will switch over to demo mode here, and I'm going to bump up the font size so this is a little easier to read. So I've created a new project here for this meetup, and everything with Suborbital and with Atmo is done using our CLI tool, which is called Subo. So to create this project, I just ran subo create project, and it sets me up with everything that I need to run a cloud native WebAssembly application. So the main file that you're presented with when you create a project is called the directive. So it's a YAML file. It can also be represented as JSON and other formats, but we default to YAML because it's familiar. And the directive is a full description of your application. So in this case, we're building a server, a REST API, that has one endpoint. This is the default, by the way. So the directive describes, what is the name of your application, the version of your application, and what version of Atmo this application is designed to work with. And you can then define a number of different things, but the only required portion of the application are your handlers. And this maps an input to a WebAssembly module to an output, or potentially multiple WebAssembly modules, because they can be chained together. So when we look at this handler, it's describing an HTTP request sent to the /hello URI with a post HTTP method, and we're using the hello world function to handle this request. So if we take a peek at the hello world function that was created for us for the basic project, we'll see that this particular function is something written in Rust. And Rust is very often thought of as the default language for WebAssembly because Rust does have extremely good support for WebAssembly, especially with the standard library and all that kind of stuff. And so that's often what we will default to. So this particular function, and in our parlance, we call them runnables. This runnable simply returns the input with hello tacked onto the beginning. So in order to run this basic application without making any changes, all I need to do is run subo build. And I pass the native flag here because I want it to use the Rust compiler that's installed on my laptop. However, subo does by default use a Docker builder. So this allows you to actually use any of the programming languages that we support without installing the compilers and the toolchains for those individual languages and learn how to configure them for WebAssembly compilation. We have figured all of that out for you, and we can instead use a Docker image to compile and run your code. So it's up to you to decide. So if I run this, you'll see, very simple. The hello world function gets built, and it gets compiled into this WebAssembly file. And then a runnables.wasm.zip bundle is created. This contains everything that Atmo would need to run my application. So it's a single file that can be distributed in order to run my application in the cloud. And the project by default also includes a Docker file that you can use to package up your application and publish it to a Docker registry. And it's extraordinarily simple. It is just the Atmo base image, copying in that bundle, and then running Atmo. About as straightforward as it can get. So in order to try out a development server, we have the sudo dev command that's built in. And so what this will do is start up an Atmo server on port 8080, and that will load our application that we've built here automatically and make it available to us. So if I kind of split my terminal and close this for a second, we can try sending a curl request to our application, and you'll see hello, my friend, is returned because that is what our function described. Now, we want to be able to take advantage of WebAssembly's great properties, one of which is the multi-language support. And so we'll pop this closed for a second and we'll turn off our server and we will create a new one. So sudo create runnable, we'll call it goodbye, and we'll say lang assembly script. Now, assembly script is a language that was designed specifically for WebAssembly that uses a syntax very, very similar to TypeScript in order to make it very easy to develop WebAssembly if you are coming from a web development background. So very similarly to the Rust function, the assembly script function just returns hello and whatever the input was. So we're going to change this to goodbye. And then we're going to run our build command again. And I'll pop out the terminal out larger so that you can see. And what's lovely about Subo is that it is able to build several different languages all in a single project. So even though we have a function written in Rust and another function written in assembly script, Subo will be able to figure that out, and it will compile them all to WebAssembly using their respective tool chains and then package them all up for the use in your application. Now, VS Code often gets mad at assembly script because it's not pure TypeScript, but it usually figures itself out after a while. So in order to try out this additional function, we're going to go back to our directive, and we're going to add a new handler to the goodbye endpoint, and we will run the goodbye function. And if we build that one last time, it will include the new version of the directive in our bundle. And if we run sudo dev again to start up our server, we can collapse that, open another terminal, and if we send my friend to localhost 8080/goodbye, you'll see that it executes the assembly script function exactly the same as if it were any other language, and we can still run the hello endpoint as well. So different languages coexisting in the same project. Very, very nice. So that's it for the demo. I would definitely suggest you go check out Atmo and give this a try for yourself. So just as a quick wrap up, because I believe we are almost at time. So what is WebAssembly? It is a binary executable format as well as a sandboxed runtime environment that allows you to take code written in various languages and execute them in a portable, performant, and secure way. Why would you care about doing this? Well, improving supply chain security, running untrusted code, building plugin systems for your applications, and executing ephemeral serverless functions are all really great use cases for WebAssembly on the server. And by the way, this is completely ignoring all of the wonderful applications of WebAssembly in the browser, which is where it originated. There are tons of use cases for WebAssembly on the client side as well. However, we focus on the server side of things. And how you can go about it, well, I've shown you one, Atmo. That's the project that we develop, and it is our main open source project. However, there are a ton of other options. You can actually use the lower level WebAssembly runtimes directly if you like. Wasm time, Wasmer, Wasm Edge, Wasm 3. There's a ton of different options. If you want to get down to the nitty gritty and execute the WebAssembly code directly, you're welcome to do so. We have another project called Reactor, which is a really nice Go library that wraps the various WebAssembly runtimes to give you all the APIs and all of the convenience things that you need to easily load and run WebAssembly in a Go application. So that's another great option. And I'd be remiss if I didn't mention the other open source platforms available for running WebAssembly in the cloud. There's Wasm Cloud, there's Lunatic, and there are some up and coming projects around the internet as well. Not to mention Cloudflare Workers and Fastly Compute at Edge both support WebAssembly for serverless edge functions. So that is everything that I have to say. If you want to follow myself or Suborbital, the company that I founded, please do. You can also check out our website, suborbital.dev. It's all WebAssembly all the time. So if this is something that interests you, you'll find plenty of things to try out and play with there. Otherwise, that's it for me. I think we have time for questions and such. I'm assuming that other folks will rejoin the stream in just a moment. If you have questions, you can throw them in the chat. I can see them and I can answer them. Unfortunately, it seems like we're having some trouble with the moderation of the questions. So it might just take a second, but you can definitely, I'm assuming you can still post comments in the chat and I can see them. I don't know where we go from there though. If you just so I can, fill the time here, we do have another open source project, which we call Atmo's younger sibling. It is called SAT, S-A-T. It is also available in our GitHub repository. So github.com/suborbital/SAT. It is a different kind of WebAssembly server. It is actually specifically designed for edge computing. So where Atmo will load many, many functions from a single application all into one instance, potentially running inside of Kubernetes or in a container. SAT, on the other hand, is designed to just load one single WebAssembly function, and it's designed to be deployed in what we call a constellation, which is a large, large group of SAT instances, and they are designed to form a mesh with each other. And they can actually execute an Atmo application by collaborating amongst each other. So there's a networked mesh created amongst the group of SAT instances, and they can all send messages between each other to run Atmo applications. So that's another thing you can check out.
So hi everybody, sorry for that delay. We had a monstrous technical issue like we tech dudes always have. So I'm gonna catch up straight with the questions, Connor, if that's okay for you.
Sure.
Okay, so one thing that interests me the most, what is the most popular use case for WebAssembly in the cloud right now? I would assume I know some of them, but I'd like to hear from someone deep in the topic.
Yeah, so right now, I think edge functions are the most popular use case, and they were popularized by the companies I mentioned a minute ago, Cloudflare and Fastly. who are both, and actually Deno as well, or Dino, however you pronounce that company name. They all have globally distributed infrastructure that can execute WebAssembly functions using various methods. Cloudflare is built on top of V8 isolates. Fastly uses the Wasm time WebAssembly runtime, and this is already a use case that is being put into production and used by some of the largest companies and products around the world. But I think the up and coming use case is this ability to run plugins and extensions built by users within cloud infrastructure. It's kind of the server side version of what Figma has done, where they run WebAssembly modules in your browser in order to create Figma plugins. We are capable of doing the same thing on the server side using WebAssembly.
Crazy cool. So something that interests me personally, I'm watching your talk, seeing you deploying a web application. So something I can reach from a web endpoint, so to say, in like no time. I'm still used to do this in Python with fast API, wrapping all that up into a Docker container, doing all the legacy registry pushing all over the place,
Right.
with CI and stuff like that. So what does that mean to containers? What you've just shown us, isn't this just containers on steroids, so to say?
Yeah. So we really believe that WebAssembly and containers, they're not enemies. It's not a replacement. We do think that they actually complement each other in a lot of ways. So and that's the reason why we ship a Docker file with every single Atmo project, right?
Yeah.
We actually expect that the majority of people these days are still shipping their software to the cloud using containers. And so running WebAssembly inside of a container makes a lot of sense, especially because within a single container, you can have many, many, many WebAssembly modules being started and stopped. And this is something that we do inside of Atmo. It's just not, totally shown to everybody because it's an implementation detail. However, Atmo is constantly auto-scaling the number of WebAssembly modules running inside of a single container to help manage the load as your server receives more and more traffic. Yeah. So I think there's really good use cases there. The one exception that I would say is that I think, in our opinion, WebAssembly is a better technology for powering edge compute specifically, because edge data centers are often very small, they're very resource constrained, and WebAssembly modules have lower overhead than a container, and so you can pack more of them into a single machine. Yeah. And so we actually believe, and we are actively working towards this world where edge compute will be largely WebAssembly, perhaps running directly on bare metal. However, that will collaborate with your central cloud deployments running in Kubernetes or whatever, where containers and WebAssembly can actually coexist in the same deployment.
That's cool. Thanks. So I would have one last question, if I'm allowed to. And now that we've seen what WebAssembly is actually capable of and where it can go and where it actually is, do you see any roadblocks in the future as it becomes more adopted to the cloud native space?
Yeah. So right now, I would say the main roadblock is that the standards around WebAssembly are still being actively worked on and tweaked and changed. And this is just a symptom of being a relatively young technology, but things are changing rapidly. And so it does require, a fair amount of work to keep up and to make sure that, not just you as a developer, but also the tools for the various languages are kept up to date to support the evolving WebAssembly standards, and especially a standard called WASI, which is the WebAssembly System Interface. And this is a standard set of host bindings that give WebAssembly runtimes access to common host functions. And this standard is very, actively being iterated and changed. And so making sure that everything stays in lockstep is going to be a challenge. And it's something that we deal with on a daily basis because we're a WebAssembly company. And so assuming the standards bodies and the different language teams and the application framework teams like ours can all stay relatively synced up with each other, everything should be okay. However, that's not always the case, and so we could very well see some issues arising from that.
Yeah, that sounds a little bit like the moving standards we see as a Kubernetes company. It's like
That's right.
You have to learn new things constantly and fix breaking changes constantly. Connor, thank you very much for answering those questions. I'm handing over to Renata and our next speaker.
My pleasure.